What's up? Welcome to Bobby Codes. Today we're going to be making music with code and math. I used to laugh at people when they used to tell me that that music had anything to do with math. And then I tried to make a music synthesizer. We're going to do some more work on the Exercism representer, and I'm going to do a couple other things to make it more fun, and I'm going to try to just kind of jump around a little bit. So if I get bogged down in one thing, I'll just move to something else. So this here is a little app that I made to explore sound files. And this is it running here. And this is just graphing. Actually, this is a sample that I found of an NES Triangle wave, which is what I'm going to be trying to do tonight. It's one of my favorite sounds in the world. You know, we should listen to it a little bit, just so that you know what I'm talking about. Let's see, Chip Player JS. What's great about this site is that it has really great, it has a speed control so that you can slow it down to hear it really well. And you know what? Yeah, so I think that's how we will actually avoid copyright issues, because we're not actually playing the entire composition. Let's see if that works. Let's see, do I need to get to NES? These are all of the games. Let's see. Oh, we're already in Nintendo. Okay, we want asterisks. And let's see, I'm going to go in the settings here. And I'm going to mute all of the tracks except for the triangle wave. And we'll just listen to that. We'll get to the track that I like. Actually, it's called Egypt. I guess that's not the track skip button. There it is. This one. That one. Okay. So what you're hearing now is what's known as triangle kicks. Actually, this has a sub bass thing that's actually making putting a sub bass on top of it. I'm going to get rid of that. So what it's doing is it's simulating drum sounds using just triangle waves. And if I slow this down, you'll actually hear how it does it. Each note is actually a descending string of notes going and it's something close to what I would say 64th notes, perhaps. And so, yeah, it's simulating a kick drum in there, and also like kind of a tom hit. And let's see, we need to this triangle wave that is being rendered here. I tried to make just my like crappy version of something like what's in Audacity. So in other words, I'll open up the repo here. It's called Mecha Wave. And here's the sample I found of the NES Triangle wave that I'll open it up in Audacity. And yeah, so there. And I can do this. Yeah, there we go. And well, what's cool about here is we can zoom in and out. But that's the entire. Yeah, it's just one sample. Okay, so this is. It's one period. So it starts at 0, goes to +1, and back down to 0, and then continues down to -1 and back up to 0. And so that it makes almost no sound, but if we loop it, let's see what happens. Let's see, I have to select loop. And how long is the note? That's but all right, so the whole idea is, well, it comes from my my favorite project. The Mario Paint sequencer. Now, notice I said sequencer. Because it actually works like, well, the closest to the Super Nintendo as far as how it's a sample player. So like here is here's one that I made. It's kind of like a ska remix of the Mega Man theme. Because once I tried to do it with the Mario Paint sounds, it just sounded weird. And somehow I got the idea to like slow it down and make it like reggae. And then it worked out alright, I think. Especially with the kiddies. Oh, you know, something's wrong with the, it hasn't loaded all the samples for some reason. If I refresh the page, it might fix that. Now, notice so that's, how is that like the Super Nintendo? Well, there's a quote from Koji Kondo, who was one of the first composers for the NES. He made the Zelda theme. And yeah, I have it down here. He said when the Super Nintendo came out,
colors from a palette of over 32,000 choices. They were poised to impress. While most of the team focused on the look and feel of the game, composer Koji Kondo had challenges of his own. With the Super Famicom, you have to create the sound samples themselves, so compared with the Famicom, it was 100 times more difficult. For Super Mario World, I decided I would try and use sounds that resembled the normal instruments you hear in the real world. So after 3 years of creative collaboration and long nights in the office, the team's efforts were about to be revealed to the world. And for Mario fans, life was about to get 16 bits better.
Introducing the next generation from Nintendo. New Super...
All right. So, yeah, he said it's 100 times harder because you have to also make the samples. It's also because when you're composing for something, well, it's like what Rich Hickey said about the choose-a-phone problem. Now, this was in Rich's Clojure talk, design, composition, and performance. No one wants to compose for a choose-a-phone ensemble, and so that's like the Super Nintendo. It's a choose-a-phone. It can play any sound that you throw at it, whereas the NES just has just a small set of basic sounds that those are the sounds that it makes, and that's it. And so that's more like composing for like a flute ensemble or something. And there's but really what I want to do is to take a step back. And the reason I call it the music education composition creation application is, well, because it teaches you about the nuts and bolts of music, how sound waves work. And that's what's so cool about Chiptune. You carve drum sounds out of white noise, and the bass is just a triangle. And by making a synthesizer, well, that's the education part. You're learning about how the music is made, but that's kind of hard. You have to do a lot of math and stuff, and it was a quicker path for me to get something that worked like this, just to make a sample player. And I did that using the Web Audio API, which can just decode an MP3 and play it at, and we're actually changing the playback rate of the note to get the different notes. And I'll have to open this up locally here to show a little bit of how that works. Let's see, this app is running currently, and that is here. And yeah, so these are the functions that use the web audio API to just create an audio buffer from an input sequence of values. And you supply the audio context, which is just right here. You define it once, and it's a dynamic variable called context. And so here I have where you can upload a file using JS file reader and just reading it into an atom as a uint8 array of bytes. This is processing the header of the WAV file. And this is what is creating the graph. This is just composing an SVG path, just a path string from a set of points. And this scales the graph. And so here is, this is the fun stuff here, where we're actually taking the input, which is just a vector of bytes, I think. And here we're creating a buffer, create buffer from the web audio API of however many frames the input is. And sampling it at 44,000 samples per second. And we have the gain set to 1/10 so that it won't blow out your speakers or your ears. And here's where we're playing it, where we connect the buffer source to the audio buffer. Yeah, then create a Clojure data structure from the JavaScript array. And yeah, we're scaling the input between -1 and 1. The values as they were, well, these are the decimal values. Interesting. So when we make the WAV file, is that what we need to scale it to? That's apparently that is how it works. We're not going to actually need to make a WAV file, believe it or not. Because it'll just be playing the buffer itself. So yeah, so that's what's on the table. I want to try to make the NES Triangle wave, which is it works. It's a 16-step counter. The reason the triangle wave doesn't have volume control is because it's creating the triangle wave with the 16-step counter, which is on all of the other channels. of the NES audio processing unit. Let's see, we need actually a better description than this, I think. Yeah, from the NES Dev Wiki. It generates a pseudo triangle wave. So this was it here. Let's see, what is the zoom? How do I zoom? Oh yeah, control 1 and 2. So yeah, I think I found this somewhere, and it was actually sampled from a real Nintendo. And you can kind of tell because of the edges of the waveform are jagged like that. But that's weird, it doesn't even start at 0, which is strange. Yeah, so it goes up 8 steps, down, and then down 8 steps. So that's what I want to try to do. And also, I have another repo called Noise, which, well, it makes noise. The white noise channel is used for creating drum sounds like hi-hats, snare drums, and sound effects like gunshots and stuff. And okay, here, so where we're creating the array for the audio buffer, we're using the JS math random function, which let's read about that function. Because we did a kind of a deep dive in pseudo-random number generators a couple months ago. And this is actually why I have such a strange interest in random numbers. If you've ever read Don Knuth's, I think it's volume 2, the semi-numerical algorithms. There's an entire Knuth chapter there. It's its own unit of measure all on random numbers. It's amazing. So, yeah, I was actually wondering how. Well, I guess that doesn't say. But anyway, so the NES white noise channel has a characteristic sound to it, just like the triangle wave does, and it does it with the linear feedback shift register algorithm. Actually, let's find that page from the NES dev as well. Yeah, then it plays it back at 16 possible different frequencies to actually. Some people actually make kick drums out of white noise. I wouldn't recommend it, but and yeah, this is a great wiki, a great source of over decades of work of people reverse engineering this hardware and just figuring out every detail of how it works. And yeah, it uses it by taking the XOR of the shift register and there's actually a it produces a specific sequence of bytes that it's actually very well known. We could actually probably search for it. Let's see. This might be interesting. This and this guy Rain Warrior, he's the maintainer of I think one of the best NES emulators, and he's one of the leading experts on the NES audio. But I think what I would be happy with for my purposes would just be to write a linear feedback shift register in Clojure. That would be fun, and use that to generate noise instead of just, and see if we can hear the difference between the JavaScript math random noise and that generated with the linear feedback shift register method. And so that's the fun stuff that I want to hit in between. Well, I did some work on the Exercism representer and actually made a draft PR. Let me try to find that. Yeah, so I got far enough that it was time to check in a code normalization script. And this is because actually I made a whole bunch of notes on this issue. So during the 6-hour stream, when was that? Last Saturday? I figured out that it would be that was a great idea that I had. I just happened to think of CLJ Kondo analysis data, and it turns out it has all of the information that we need, I'm pretty sure. And so my original idea was to find all of the positions of the identifier names that need to be replaced. And I was getting funny results. And I think I realized why. It's because once we edit the source code tree, that changes the code that it represents, which then changes the positions of everything. So I think the whole idea of using the position data is not going to work at all. But that's kind of a cheesy way to do it anyway. What we want to do is, and the whole point of using a parse tree is to be able to search through the code structurally. And so this is my test case that I have now. And I tried to cover some edge cases that I thought of using the function. Well, there's a function in Clojure called name, which right here, you call name on a keyword, and it gives you a string. It's the name of the key. And so it's a Clojure function from clojure.core called name. And so we need to make sure that a usage like that this would not be touched, or else that would be incorrect. That we would be not replacing not a local but a core function, and also, well, there's name as part of the function, part of the function name, and here we have name inside a string. So clearly we couldn't just do a regex find and replace. That would be way too barbaric. And we're in luck because this name, which is not a local, does not appear on the list of locals from the analyzer. We just need to set locals and arg lists to true in the analysis configuration, and then the arg lists show up under var definitions, and this is an example of one. So what we were doing originally, so yeah, here's the arities, which would be the first name to be replaced in this snippet would be right here, the first argument to the function with name. And so it would make sense to figure out how to take care of all the arities first. And so the original idea was, well, to use the position data, where we could find the name end, column, and row, and we could navigate to that position, but we don't want to do that. So instead, we're going to navigate to the name, and then from there go to the next vector and find it in the vector. And yeah, so then I made it even harder and made it a multi-arity function. So here we need to replace name here and here. and not anywhere else. Oh, I forgot I forgot to paste the other section here. Oh, that's fine. It's already there. But and this was how we would replace the node. So we're just finding the next value with the name of the var definition that we're passing in here, and then going to the first of the arguments, which is from the arglist strings key, replacing it with the symbol placeholder 1, and then printing it out, and this is the output. And so we can see that worked. We have placeholder 1 as the first arity, the unary arity. And so then we just need to do likewise for the rest of the args, and then move on to the locals. So I figured it was time to generate the map of placeholder names so that we know what to replace them with. And so here I'm getting all of the picking apart all of the arg lists and then turning that into a set of strings so that there's no duplicates. And this is really important, actually, to go back to the Exercism docs, because I posted a question in our Slack, because I realized that there were different possible strategies for the name mappings, because how do you consider scope? Say someone writes 2 global functions and each take a single parameter x. Does that get 1 name or 2? They only use 1, x, but x is 2 different, it points to 2 different things. And so I was thinking that a possibly more technically correct way to do it would be to only replace those names that are in that scope. But it turns out that's not the way we're doing it. And it says right here, all identical names must be replaced with the same placeholder irrespective of scope. Which is actually much easier so we just have the set of strings that represent the args. We'll worry about the locals after this. First we want to just try to replace all of the arguments. And so here we're generating the list of placeholders, which just starts with 1. And, well, this sorts the placeholder names. And in the mapping JSON, it's the placeholders mapped to the original names. Because that's where we're using to replace them back to get the original names back. But I switched it for the output that's actually stored in the variable so that it's mapping the original names to the placeholders. And so that is how far I got. Now, let's open this up. Alright, so we'll fire this up by starting a REPL with Babashka. And now we're analyzing the test code, which is right here. Yeah, so we already saw that. Yeah, so these are all the, this is producing a map of the name and the row and column of the local usages. But we're going to put that on the back burner for now. So this creates the placeholders. There's just two arguments to be replaced, name and color, which so there's two occurrences of name, and we want to make sure that it skips over this one, which is the usage of that arity. Okay, so this creates the zipper from the source code. And when I was trying to figure out how to actually iterate this, it's making my head spin, actually. And that's why I think I need to make some music once I get stuck, as like a palette cleanser or something, because there's different way. I think I kind of just want to write a reducing function so that we could just pass it the collection of names to be replaced, and then just pass that to reduce. But for some reason, I'm not sure if that is the right way to do it with zippers. There's the walk functions, which could be used. Let's take a look at that. Where is he? It's in the zip API, where post walk. let's actually look at the example usage of that. And there's this little gotcha here where you have to make sure you go up before you walk, so that you're back up out of the list, I guess. And so we would write these functions for how to select whether a node should be edited. And if we did that, then how would that work? We would need to generate some map of each of the names and how to find it in the code. So, yeah, how would that work? Let's try to explore the zipper a little bit. And I'll create a function pipeline here. And we'll just print out, well, the whole thing for now. It's not a huge amount of code, so I should be able to find the beginning here in a reasonable amount of time. Okay. What we have is, well, there's node interrogation functions, but we would need to whoops. Let's take a look at those. In the node API, we have node interrogation, where each one has a tag, inner, the children. Now, actually, what we want is to find to look back up the tree and find the parents, so that we could locate each name by the node that it's in, by tag or something, and that it's also located inside a given parent node. But to do that, we would have to do something. I read something about how to traverse the tree and be able to find back where you were. Yeah. When you're interested in restoring your location after digging down deep to make a change. Well, actually, we just want to explore to ensure that that a certain node fulfills whatever predicates we write. And so that's one way. But that actually seems like that would be harder than the other way that I was thinking, which was, what was the other idea before that? To not use the walk, but yeah, to just reduce over the list of names. And then we can just have a simple scheme to be able to find the args and then to find everything else, whether it's a local or yeah, it's going to be either an arg or a local, right? So this is how we would find the first name. So here we have the list here, name, and color. And yeah, I'll put this in here. And so we just used find value to do a depth first search with Z next to find the name of the var definition, which is this here. I can just evaluate this. And that was picked apart from this arg list strings here. And okay, yeah, so it was this here. So it just finds the var definition, then finds the next tag that is a vector node, and then finds the symbol name. Okay, so that this is just testing that. And then it prints out the node. And let's go ahead and replace it. It looks like here is where this is where I was thinking of writing a reducing function. And but first, just to make sure that yeah, why wouldn't that work? I'm gonna create a new zipper that would be the result of replacing the first one. And okay, so that worked. And yeah, so that's how far I got earlier. And all right, so just to actually get the new zipper, I think I would just do it like this. So define this as zip 1. And we could oh, that's interesting. Okay, that's why I had the up. So at this point, we were still down the tree where we left off, I guess. Okay, so do we want to just get the root? Yeah, I think we need to call root. Do we just go up after that? I don't know. Yeah, then it just went up 1. How do we just go back up to the top of the zip? Would that be leftmost? Let's see how they do it. Here they're calling root string. There was somewhere where it talked about how sometimes after you make a change, you feed it into a new zipper. So let's see how they did that. We might have to actually explicitly create a new zipper. After making changes, yeah, here we go. Less frequently, one might call root, which affects changes and returns the root rewrite CLJ node. But I did that before, and so yeah, what is it? Forms node cannot be cast to a function. Where am I? A forms node. Can I just evaluate this? Yeah, so it looks like it's here. What if I call root string? There it is with our placeholder. Pass the original zip options on creation of new zipper. So maybe we... What is the zip Eden function? Oh, so it creates a zipper from a node. Let's see what print root does. We're getting nil. Why is that? So why can't we call node here? That's maybe we need to go next. No. Right. No. We need to go back up. How do we just go back to the beginning? Okay, so that's where previous is how to return after the previous depth first movement, which that's what we did. Okay, well, if we used leftmost, why isn't there an upmost? Yeah, so that didn't even... So we need to go up. What if we did previous, and then we're back to the var definition, but we did 3 searches, so that's confusing. Yeah, it's just doing one step at a time. How do we just get back to the beginning? This shouldn't be difficult. Maybe what we want to do is sub-edit. here we're iterating next. So that navigates you to the end node. So we could iterate previous, I guess. Maybe we just want to stay where we are. Oh, now how about that? Well, because... Well, then we know that we're in the var that we need already. So, yeah, maybe that would be good enough. All right, so zip1 is at placeholder 1. And okay, so but then, oh, okay, so that still works. And I'll print it. So here we have this here, and so zip1 is located there. And so then we would need to find the second name. Now, it could just be in the same vector with it. Except we know it's not because we just replaced one called name. But we don't want our function to have to know that. We do know that we are still in the vector, though, because we haven't left it. Maybe we should actually go back up. So then we know that we're in the vector. And if we went up again, it seems like that would actually be the best thing to do. Because then we would be set up where we need to be for the next iteration. So I think that makes sense. So here's where I'm trying to make the generalized replace args function, which this shouldn't say impl, it should just be z, so that we know that it's just referring to any zipper that is passed in. And after we replace the symbol, which we know is in a vector, will go up twice. And, oh, wait a minute. This isn't... I was trying to use loop, to loop through the args. That is the list of args that we'll be looping through. Whoa, what's going on? Oh yeah, that needs a var definition. And name color. Okay, so let's say so this will take any zipper and so does this take the var definition how do we know that we're in the right var? That's and does it get past the list of args, or what we'll have to do is like to create a sequence of maps, I think. Out of this. Well, actually, let's see. Like, how do we find out what var we're in? This is making my head spin, and I want to see more examples. Okay, so what is the arg that we would find? Well, we would be looking for the next name. Maybe this would we just need one function that would deal with one var definition. And then we could reduce that, and then reduce that through the list of var definitions. Maybe that would work. And so we would just change this one to args, okay. But then how do we know? We could pass it a list of args. Each one would be a map with the var that it's under. No, we wouldn't even yeah, because we need to. It would be assumed that we're already in the var that it's passed. Okay. And so let's get rid of this and just find the next vector. Okay. And so let me make that clear here. This takes a zipper currently located at well, here it's a list. So it's before the vector. And actually, this will just it'll just take a single arg. And to actually find the right placeholder name, we'll look it up in the map of placeholders. So we would say we would get from placeholders whatever the arg is. So this would be passed name What happens if we actually because that would be wanting a string, and at this point arg is a symbol, so let's yeah. Yeah, so that gets our string and then turns it back into a symbol. And so we pass it our zipper. And the first arg, which would be, it gets a symbol, so and so this would be the zipper after the first iteration. And there it is replaced. And if we see the node that we're currently at, so there we are, before the vector containing placeholder 1, and ready for the next one. So, which would be to find the next name. So let's try that. So can I store this in a var called before I was using zip1. Yeah, okay, so that works. And so now, let's see if we can do this again, but with zip 1 instead of impl. Yeah, we want that, and then root string and print line. And okay, so that's interesting. It went to the vector. But then it put it. Yeah, so that's interesting. How do we make it so that it, because it could have been in that vector. We need to somehow make sure that we're still in a vector or to keep going. So when we find the value, we actually need to use the more generic find function. Oops. Yeah, I think we want find depth first, or just find next. Well, that goes right, or next. So I guess would find next using the next movement function be the same as find depth first? There's so many functions. Here we can test if the current node is a vector. Will that help us? Let's see. So we're in zip 1. And then we would find the next vector. Here we'll and we could look at the children. So the next thing would be to find the value of the next arg. But actually we don't want to do that because the next one is not in a vector. And yeah, so we need to keep going. So we'll go to the next value containing symbol name. And go back up. Does that make sense? And then test if it's a vector. That's not going to work because and we get false. So if we're not in a vector, then we need to go to the next vector. Does this even make sense? How do we pass this to current node again? That's all right. I think this is why I thought it would be a good idea to switch around when it gets to this point. Because, yeah, I getting kind of bogged down with that, and I'm not sure why. I guess I just need to learn more about zippers. Alright, so let's try to make a triangle wave. I think I will use this one. This is the Mecha Wave. And this is a Shadow CLJS project. And here was where I recorded an audio file, just me saying mic check. And I'll just go ahead and play that.
Mic check.
Yep, that's me saying mic check.
Mic check.
And so now we could load this. And we could choose the file. Mic check. And it rendered a little wave for us. And so, yeah, this is a whole bunch of values ranging and okay, so here
Mic check.
and that works. So it's taking the bytes that were, well, that I have Clojure functions that are decoding it here, and then it's feeding it back as a buffer back into the web audio API,
Mic check.
and it's pretty much preserved. It's not perfect, but so let's try to explore it in the editor now. So that file is stored in this atom, file atom. And here's a scale function which is going to come in handy. Okay, yeah, so I had a play button. Where's the, yeah, so when I hit the play button, that uses the play function, which takes the file atom. Oh, I missed it. And yeah, so this is using the scale function to scale it between -1 and 1, which is what the audio buffer needs to be. And what we're going to do is just try to make a 16-step counter. Well, so that would just be range 16. And then what we would do is calculate how many times to repeat the sample of each level in order to achieve the frequency that we're looking for. So if we did there's probably another function that does this actually. Repeat takes the collection. Yeah. And say we repeat each one twice. That's not what I was expecting. Let's see. Okay, yeah, that's how do we turn just a and we could do, oh, let's just do map cat. Yeah. And we would take, so instead of repeating each one twice, we would actually, if it was, so there's 44,100 samples. And that represents 1 second of audio. And so if we took a note that we wanted to make, how about, this is a bass line. So say we want frequency of 100. Let's take a look at our triangle wave. So this is not a second, obviously, but if it were, just pretend that this is a second for a second, then there would be 1, 2, 3, 4, 5, 6, 7, 8 steps. Yeah. Then that would be 1 hertz. And so there's actually 8, 16, 24, 32. So I guess we would divide 44.1 by 32. Does that make sense? And so that would tell us how many samples each step would need to be for 1 hertz. And so then we would divide that by whatever frequency we want. So say 100. And I'm not sure if that's going to work, actually. It would really be that few samples? I don't think that makes sense. Let's take a look at the running app here, and I'll put the NES Triangle wave back in. And so here we have what I could do is actually record a second of I think and this is, it looks like not showing the entire thing. And I wonder why that is. Let's see what's maybe it's the view box. Let's see. This is so this is chopping the data into parts. Wow, this is confusing. It's extracting the music data. Let's take a look at the values in the file atom. And oh yeah, so that's already what I'm doing here. We'll make a similar function to this here. Where we just use buffer source and audio buffer. And yeah, so that's what actually plays it. And yeah, let's just see if we can throw some stuff at the audio engine. Let's go over this this calculation once more. So if this was 1 second, then this wave would be 1 hertz. And there's 32 steps. And so each one of these, there's something that doesn't make sense, that it's kilohertz. No. It doesn't make sense that it would be that few samples, I don't think. And we wouldn't be able to get it that precise anyway. But if we repeated each one 13 times, that's what it would look like. And then we could scale that between -1 and 1. And here we have so it starts at 1. And okay, so we want to reverse it. So now we actually want it to start at 0, right? What we could do is just go from -8 to +8. And then we would repeat this for however long it would take to make a second. And, well, we would need 44,000 samples. So since there's 16 times 13, so that's how many times we would need to repeat it. And let's see, there is the cycle function that will just do that as an infinite sequence, and then we can take 44,100 of them. And so I'll define this as NES Triangle. And yep, that's expecting a Clojure data structure. So, are ready to try this and see if we get it sound? Okay, audio buffer actually needs something else. Oh, yeah, it needs the audio context. Okay, so I didn't hear anything. Maybe it's just taking forever because it's Clojure script. Yeah, it timed out. Interesting. So yeah, we probably need to use a JavaScript array like we did right here. Let's just try it with a shorter file. Or a shorter sequence. How about just like 1,000 of them? Oh, yeah, we are disconnected at this point. Oh, look at that. It actually made we heard something eventually. And it sounded like a note. Okay, it just took forever because it had to process 44,000 samples through Clojure with a Clojure script sequences, which are not very fast. So I guess is this still running or? Yeah, okay. So I'm surprised that we actually got a real note. Let's try playing a shorter one. And I haven't heard anything yet. Is it gonna make a sound? It returned the audio buffer source node. Is that what it was supposed to do? I'm trying it again. It could be that we lost our audio context. Let's see. There's the mic check file.
Mic check.
Oh, and we just heard the triangle wave. It was just a little blip. We could try rendering that on the screen. All right, so how can we do this with the JavaScript array instead? Because then what I can do is take this here and it'll be 44,100 samples, and I'll plug this into a we have a Clojure script to JavaScript translator, but I want to make sure that it's the right one. It's called It was Mauricio's repo. Let's see. Oh, here it is. Oh, I just lost it. There it is. Oh, this is the other way. If I just take this and let's see. There's the Clips app that does what I'm looking for, I think. Okay, so it looks like we put Clojure code in here. And press Control Enter. No. Oh yeah, so this is not what we want at all. It's like weird Google Clojure compiler. Let's just search for, let's see. JavaScript array. With the same element repeated multiple times. It seems strange that I would have to do it that way. Is ClojureScript really that slow? Just to copy this sequence into an audio buffer. Now, actually, what I could do, yeah, no one said that we have to do that in real time. So let's And all right, so that's using the audio buffer. And that's actually doing what we wanted and setting, it's creating a JavaScript array of length 44,100. And then setting each element and then returning it. And so it seems like we should be good to go. So if we said oh, now why was it so short? Is it because I didn't define this? So that'd be yeah, so this takes a little while, which is fine because this would be part of the loading phase. Oh, and it timed out. Ah. Let's see. So, are we dead? Might need to just refresh the page. Well, it looks like that caused the whole thing to crash. Well, let's see. I guess we'll trash that. Put a pin in it, come back in a little bit. Now, I think I've got some energy left to play with the representer just a little bit more. And, oh yeah, that's the one that we open up in WSL. And, My heart sinks just looking at this stuff. These zippers are, I got the zipper blues. It would be cool to talk to someone who's more familiar with using rewrite CLJ than I. Because it seems like there's some key things that I'm not getting. But let's I'll connect and we'll just play around for a little bit. Yeah, I don't know. I think I might wrap this up. Because apparently my brain is a bit fried. Even for making music. So let's see, which one of these was because that was after the one so that's after the first one was replaced. And it went up twice. And so then when we feed that back, and then go return to the vector where we last were, and then go to the next symbol name. At that point, let's not go up just yet. And in fact, let's not go to that value yet either. And what we'll do here is we'll inspect the children of the vector. And we would do that with, let's see, child S expressions. Yeah, let's see if that works. And yeah, so now we know that that is that's interesting. It's that it put it in a list instead of a vector. And so we want to see if this contains the name that we're looking for, which is passed in as arg. And so how do we inspect the values of so that's what just gives us the vector. That's interesting. But we want to I guess we want to go down into the vector. Next would do that. And then so basically we're looking for the next node. We need to make sure that the node that we find is the value that we're looking for and that we're still in the vector, or else, okay, so maybe this would be a sub-edit? That subtree editing seemed like it might be what we want. what we could do is we could create a list of each vector and the names that should go in them. How about that? Well, actually, wow, that might have been the best idea I had all day. And actually, we want to back up before that, and we will just get the raw vectors. Like that. So then we will map Eden read string and so now we have a list of our two vectors. We could map them to the names that that they need to be. Which is already done in our placeholders function. So we'll navigate to the name of the var that we're currently dealing with. And go to the next vector. Then we will get the child expressions, and we can see it's just name. And actually, let's just get the S expression. So it's name in a vector. And we want to find out if that matches the one that we're looking for. So how do we need to write some kind of special predicate that will I guess we can just use what if we just found the next value that okay, so yeah, it finds one that would S expression to, let's just try first args. No? Actually, what were our args? Oh, yeah, I was trying to, not there, here. Yeah, so that should... That is the S expression that we're looking for. So, yeah, why isn't it finding it? That's, oh, maybe because we didn't... No, that should still find it. Find value doesn't seem to be working the way I would expect. The first token node. All right, so let's try this with a different predicate. What are the find? Take a look at the find functions. So what kind of predicates can we use? So we'll first we'll find the var that we're looking for at least. And we could navigate to the next node that is a vector node. Find next depth first. You know, where that function is used, so that we could see an example, is actually in the Clojure test runner. So, yeah, so this is using a predicate to find out if it's an assertion. So I think we should, and what was the navigation function that? Just the default one. So it's just going, oh, no, that one doesn't take it doesn't take a navigation function, it just does next depth first, which is what we want. So say we get to the vector. We know it's a vector. We want to know. See, I thought I tried this before, and like to get the child expressions. What is just value? It's the token name. And that's deprecated. I think that's just S expression. let's say we have this whole thing. The zipper zipped up at the vector. And then so it's zipper at the vector. And so we would say and it's false, but why? I evaluate that. Oh, and it's symbol name in a vector. Okay, you know, maybe we're getting somewhere. Now it says true. Okay. So instead of name here, it would be whatever the args are that are currently being replaced. So first args. Actually, that is a symbol. So if we just said, and this would be our predicate function. To see if let's see, do I put the percent sign here? Or I guess we'll find out. But yeah, this is what, oh, wait a minute. What did I? There's too many of these. I'm getting confused. And anyway, it didn't find it. Maybe we just need the percent sign there. Nope. Now that seems strange for some reason. Because there it is. And yet, if we say first args, that should be the same thing. I guess we weren't supposed... Wait a minute. Let's not find the next tag, I guess. And then try this. Ah, okay. Did we just get somewhere? I think we might have got somewhere. Wait. No. Are we at a node at all? No, what's going on? Okay, maybe it didn't find anything there? How? I don't know what the problem would be with that. So what we're doing here because remember we tested it to see if we went to the node right there. I got the zipper blues. that what was just... I think we used child expressions as well, I believe. Maybe that's what we need to do, is create a subzipper. Oh, there's child expressions. All right, so why could do what we did before? Was I created a var with remember it was called zvec, and it's at a vector node. And the predicate we used was, well, this one, right? Did we not? Let's just take zvec and let's read the docs for this again. Let's see. Starts depth first after the current node. So it might be we just need to not have this. Yeah, don't find the next vector. Just stay there. Wait. Maybe we need... Huh. Remember when I had symbol name? And that oh, look, we got something. Oh, okay, interesting. Wait, so why is symbol name different from if we do first args? All right, so at least we discovered the issue, but why is symbol first args maybe? Ah, because it's in a vector already. We want first args without the vector. Aha, okay. Might have just gotten a tiny bit closer. Okay. So let's see, I actually want to make this more generic so that it will just take one arg. And so we're going to have we're going to generate from our analysis data a list of it'll be something like this. And let's see. This would be not all of them, but just the ones for one of the var definitions. And we would do that for all of them, I guess. So the var defs would be that, and And then we would just map them? Is that we would make this a function, this whole thing, and do that on all of these. Let's see if that makes any sense. Apparently not. Yeah, because we didn't pass it anything. All right. And let's see. Actually, we want to do something different. Let's just have this do it on one. We'll make this a function that will extract the arg lists from a var definition. And then we would call that on, well, we would map it on all of them. And actually map cat, maybe? Yeah. But what we want to do is find the name of the definition. You know, we could actually just pass the, wait, no. We want to take What I want to do is build a map for each one, I think. I guess I could pass it to zip map, but then we would like repeat the actually we need that done by the first one. What does regular arg lists look like again? Oh, yeah, arg list is a function. It throws away extra stuff, so we can just repeat the, we can use that as the keys, and then the vowels, well actually I want those to be the vowels, and the keys will be, we can just repeat the name of the vardef, so we would have the lists. And then we could count the lists. Yeah, that's fine. We'll say repeat it, the count of the lists. And then map that to the lists. I don't know, does that make sense? No. Oh, because... And we still didn't get... I might be using repeat wrong. No, apparently not. Right, so... Oh, you know that... Gosh, I should probably, like, go to bed or something. Okay, so, well, that's actually not even... Oh, because we're not counting the lists, because... yeah, so that... yeah, so that gives us 2. So then... if we took... yeah, the name is fine. It didn't... this isn't repeating it. It must not be repeating it enough times. Yeah, so why wouldn't that... and then we'd be calling it on this. With name. So why isn't it... why isn't it mapping it right? Oh, because you can't have a... oh my god. You can't have a map with multiple keys. We want a map for each one. So we'll say into a vector we'll go a map. No. So yeah, for each list in lists, we'll output a map with the name of the first and so let's see, the key will be the var will be that, and the args will be whatever the list is. Okay, so then, yeah, that will be the body of our arglists function. And I'll change the var def to be that. Is that right? It didn't format for some reason. Why is not... Alright, so then we would call it like this. Alright, so was this what we were doing before? Wow. What is the one that... And yeah, actually, I think we would want to do that. And yeah, so then we have all of the vars to be replaced, or all of the args to be replaced in the whole source code. All right, so what's going on here? So now we can take so if we want a function, it would be like this, but since we're not going to do it like this, I'll just edit this one. Or I'll just make this a new function here. Replace arg, and this will actually be, it'll take the keys I'll do that. Yeah, I think I will do it that way. Except that it's going to take a zipper at a certain point. And it will take an arg, which is currently going to be passed in as a map. And yeah, we're no longer using this, and we're actually not using var_def either. The name is going to be the var key of the arg. So we'll find that, and oh, wait a minute. Yeah, this is right. And we'll take, this is going to be the args of arg, wait. It's an arg list, so that makes more sense. Oh, yeah. And the args of the arg list. And then we would say replace arg actually replace arg list makes more sense. And we'll take our source code, and the one that we wanted to find is this. Yeah, to replace. And yeah. So yeah, it found the vector that we need to replace. Cool. And then we just need to replace the child. So is there a special way to do that? Oh, Eric just approved the PR for the Clojure test runner, where I bumped the Babashka version. So now the I think all of the rest of the Java methods are supported, which is great because that'll give people less confusion. It should be fine if we just do replace that node with the arg list. Which is so we replace that with the args of arg list. And then wait. We just replaced it with the same thing. we want to take that and look up each one. So we have to, so that will give us the vector to be replaced, and then we need to, so that would look something like this. Symbol name And let's say there's also a symbol color. Name color. And so we would look that up in the placeholder map. So we would say so we would do something with this. We would look this up. We'd get that from the placeholders. Now, we don't want the symbol. We just want, so then we would have to turn it back into a string. And so this would be whatever the thing is that, so that we would map does this even make sense? I don't know if this makes sense. Map V. Yeah, okay. Except we want to after we get the placeholders, it needs to be a symbol. Okay. And so instead of name and color, that is the args of arglist, right? Wait. Yeah. Wow. I'll print out that node, and it's a vector with, oh no, wait, yeah, that is what we wanted. All right, so let's define this as zip1. Which has the first one replaced. And And there it is again. Okay. So then we would do something like this again. On the second of the arg lists. And then this would be something that we could map. I'll just evaluate this just to make sure that, yeah, so the second one is the arg list that has name and color. And yeah, I guess we'll just try this. Print out that node. And cool. Wow. Okay, I just got a little bit farther. Amazing. Okay. So indeed, we would where I make arg lists. And then I'm map cutting it over the var definitions, which, yeah, I guess that makes sense. All right, so we can't map it, we need to reduce it. Reduce, replace arg list. We pass it our original zipper and we map it over this. Or reduce that collection. And let's see if that does what we want. In order to find out, we'll just go z root string and print line. And no, see, okay, what is the problem? It's not reducing it right. Am I doing something wrong? It just gave us the second one. So when it, and yeah, see, maybe we need to call root. You know, that might actually be it. No, but why didn't it? Huh. Huh, you know, maybe that's not a collection we can actually... no, so that... maybe we can't reduce over that? Oh, that wouldn't make sense. Of course you can reduce a map. That's, Oh, you know what? That's why. I'm glad I noticed that before I gave up. Boom. Excellent. Okay, wow. Okay, I'm gonna clean up this code and check it in, because, wow. This is so ridiculous, but at least I got somewhere. We replaced all the ARG lists without any of the other stuff. Alright, get rid of all this. Okay. Get rid of this. Bye-bye. Don't want any of this. Don't want any of... yeah, any of this. All right, that's all of the junk that now save this, and all right, get to recap what what I've accomplished over this stream. Maybe that whole business with the making the music actually somehow did the trick. It kept me from burning out. It was like the palate cleanser. Okay, so this I'm going to see if we can ask Calva to thread this for us. Do a thread first all. Yay. Alright. Huh, now that actually looks weird. It looks weird with the call to reduce, but okay, I guess. Yeah, I actually just want to And, you know, I should really, the arglists function. We should probably just make this a, I think it's actually important that it's the arglists of just a particular var definition. Oh, wait a minute. We'll have to make sure that this works with multiple top-level forms. But this is good enough for now. And yeah, I'll just add this to the PR here on the site. So, and yeah, we'll go to my patch. And all right, so there's the new code. I'll call this replace arglists. All right, wow. So, thanks to those of you who joined us today for this episode of Bobby Codes. Visit my Patreon if you want. Patreon.com/Bobby Codes. BOBBI Codes. And we'll finish figuring out how to make these Nintendo sounds sometime. And we'll do some more work on the Clojure representer. Till then, stay as stress-free as you possibly can. Alright, so next time we'll work on replacing the locals. And who knows what other trouble we'll get into. We'll see y'all later.